All right, this is section 6.2. We're looking at the binomial probability distribution, and you can see our objectives there. Determine whether a probability experiment is a binomial experiment, compute some probabilities, compute means, standard deviations, and then graph. So let's talk about what is this thing. Determining whether a probability experiment is a binomial experiment. So in section 6.1, so the previous section, we stated that probability distributions could be presented using tables, graphs, or even mathematical formulas. So in this section, we are going to introduce a very specific type of discrete probability distribution that can be used or presented with a formula, and it is called the binomial probability distribution. Okay. Now, the binomial probability distribution is a discrete probability distribution that describes probabilities for events in which there are two mutually exclusive or disjoint outcomes. They're generally referred to as a success or a failure, such as making a free throw or missing a free throw. But we actually will need to define what the success is and what the failure is, because a failure could be making a free throw if you term it that way. So we just have to define what we mean by a success. Okay. So experiments in which only two outcomes are possible are referred to as binomial experiments, provided that certain criteria are met. And here's the criteria that we need. So, and again, this little prefix here, bi, just means two. So two outcomes. So we are a binomial experiment if the experiment is performed a fixed number of times. Okay, meaning it only happens, we only do the experiment 25 times or 50 or 13. It's not until we get a certain number of successes. We're going to do this many trials and we're going to see how many successes we get. So each repetition of the experiment is called a trial. Now, the trials need to be independent, meaning one trial doesn't affect the other, and each trial there are only two mutually exclusive or disjoint outcomes, so success or failure. Those are the only two options, and we kind of define what's the success and what's the failure based off of the context. And then we need the probability of success, and that's got to be the same for each trial. So that probability for success cannot change. So here's some of the notation. So we're going to say N independent trials. P is going to denote the probability of success. So then 1 minus P, the complement, will be the probability of failure. So if you have a 60% probability for success, then 100% minus 60%, or 1 minus 0.60, it's going to be 4.4 or 40%. Okay, and then X denotes the number of successes in independent trials. Okay, so X, whatever we're looking at, say the probability that we get exactly 3, that has to be somewhere between 0 and n. So if we do 26 trials, you can't say what's the probability of getting 28, because again, the actual experiment, the actual number of times something occurs, can't be more than the actual number of trials that we look at. Okay, and I mentioned this before, so just note that the word success does not necessarily imply something positive. Success just means that an outcome has occurred that corresponds with that probability P, or the probability of success. So for example, probability experiment might be to randomly select 10 18-year-old male drivers. X could denote the number who have been involved in an accident within the last year, and a success would mean obtaining an 18-year-old male who was involved in an accident. So I know that sounds horrible, but again, we're just defining what is the success, so that when we set up our formula, we know what we're looking for. So we define what the success is. Okay, the outcome obviously in this one is not positive. We don't want to see accidents with 18-year-old male drivers, but in terms of our experiment, it's a success. meaning that it happened. What we were looking for happened. So let's look at a couple of examples. So determine whether the following probabilities represent a binomial experiment. If the probability experiment is not binomial, let's state why. So a random sample of 30 cars in a used car lot is obtained, and their mileage, those are recorded. Okay, so this is definitely not binomial because there's no way to define a success. Because we do, every car is going to have, we've got a fixed number of trials. We're good there. And they're most likely independent, but we don't have two mutually exclusive outcomes. We're just going to record the, we're going to record the mileage. And the other problem here is the variable is continuous. Okay, the number of miles is continuous. So binomial is a discrete probability distribution, and mileage on a car is a continuous variable. So that one's not going to work out for us. So the next one, a poll of 1,200 residents is conducted in which the respondents are asked whether they believe Congress should reform Social Security. Okay, this one would definitely be a binomial because we have a fixed number of trials. We can assume they're independent, and there's two outcomes. They either believe that they should reform Social Security or they don't. So, that could be success and failure. Okay, 14, a baseball player who reaches base safely 30% of the time is allowed to bat until he reaches base safely for the third time. The number of at-bats required is recorded. Okay, in this one, we are not binomial because we don't have a fixed number of trials. N is unknown. So they're going until they get a certain outcome, and that's actually not going to work out for us. So N is unknown, or it's not fixed. Okay, there's another distribution. It's called a geometric distribution that might work for the first time, and then a negative binomial, I believe, would take care of this 14. But for the regular binomial, that's not going to work out. Okay, the next one, 100 randomly selected U.S. parents. So we've got a fixed number of trials, so that's good there. With at least one child under the age of 18 are surveyed and asked if they have ever spanked their child. The number of parents who have spanked their child is recorded. Okay, this looks to be binomial because we have a fixed number. We can assume independence. And then we have two possible outcomes. Either they spank the child or not. So in this case, we'd most likely, again, this is where it seems counterintuitive, we'd most likely put a success as those who spanked their child and a failure as those who did not. But again, it's just for the purpose of differentiating our data. And we're not saying that it's successful when a parent spanks their child. As far as in the general sense of life, but again, that's just how we say, okay, it happened, therefore it's a success. We're just looking at whether the outcome occurred. Cool. So a binomial distribution, here's the function. So the probability of obtaining X successes in N trials, if you are a binomial experiment, is N choose X times your probability for success raised to the X power times 1 minus P, which is your probability of failure, to the N minus X power. Again, X can be anything between 0 and your total number of trials. And these calculations are going to get big in a hurry, so we are going to use StatCrunch to get these. But I'll just show you a basic one as to how this works. So we have a certain basketball player makes 75% of his free throws. So in that case, the probability of success for us is going to be 75% or 0.75. Find the probability that he makes exactly 2 out of 3 free throws. So that means that the number of trials N equals 3, and the value X, we're looking for 2 successes. So this is, what's the probability of 2 successes? Okay, so then it's N choose X, so 3 choose 2, times our probability, 0.75, raised to the x power, which is 2, times 1 minus 0.75, which is 0.25, to the 3 minus 2 power. Okay, so to be a little bit more simple, you would do 3 choose 2 times 0.75 to the second, and then times 0.25 to the first. And this would be 0.4219. So there's a 42.19% chance that someone who shoots 75% in free throws will make exactly 2 out of the 3 free throws. And that's just an example of our probability distribution function. Now we're going to use StatCrunch to start doing some of these, because the number of combinations, those are going to get pretty big, and it's going to be more simplistic for us. Because our focus here is not can you actually do the calculation, it's can you identify that it's binomial or not, can you identify what our parameters are, and can you give me the actual probability in the end, not can you calculate the probability, because the computer will do a great job of that. So in these questions, we have a binomial probability experiment is conducted with the given parameters, and we want to compute the probability of X successes in N independent trials. So we've got this first one, N is 50. The probability of success is 2, and we want to know what's the probability that it should be 0.02, that we get exactly 3. So I'm going to come over here into StatCrunch. Okay, and let's see, under calculators, there's binomial. So in binomial, we want N was 50, our probability of success was 0.02, and now we want this to be exactly equal to 3. And when I compute that, I get a probability of 0.0607, we'll call it. Okay. So, whoops, not using the highlighter there. So the probability that you get exactly 3, sorry about that, was 0.0607. And if you were to try and do that in your calculator, you'd get an overload. You'd probably get a memory error. I think I jumped over the top of this. There are going to be some phrases that you run into that you want to be able to identify. So when you see something like at least, no less than, or greater than or equal to, that's when you're going to be using a greater than or equal to sign. If you see more than or greater than, you're going to be using a greater than, and so on. You might want to pause the video if you need to review those, but you will need to be able to identify in the reading, because it might not say greater than or equal to, it might just say at least. And you have to identify, okay, at least 2 means 2 and everything above. Or more than 2 is everything above 2. So you have to be very careful in understanding those. Okay, here's another one we want to know. When N is 2, probability of success is 0.2, and X is less than or equal to 3. So that means we could have 3 successes, 2, 1, or 0. We're going to add all of those up. So over in StatCrunch, again, I'll show you where we grab this. So it was under calculator, binomial, and N was 9. Probability of success was 0.2. And we wanted X less than or equal to 3. So again, this is going to sum up, and you can see it in red. It's going to be 3, 2, 1, and 0. So that probably is 0.1 or 0.9144. So we would say that the probability that X is less than or equal to 3, this is the same as the probability of getting a 3 plus the probability of getting a 2 plus the probability of getting a 1 plus the probability of getting a 0. So it's going to add all of those up. It's going to sum them all together, which is 0.9144. So we'll continue this discussion on binomial experiments in part 2.